Alright, this lesson number 8, we're moving more from the theoretical stuff into how we can actually use this, and in particular how it relates to us heating the Earth. So we've got the Earth, there's the Earth, and there's us. And so what happens is that we've got the sun up here. Sun has some radiation, and so of course around the Earth we've got the atmosphere, and so some of that radiation from the sun gets released, some of it gets reflected back out, some of it just gets absorbed into the atmosphere. So of the amount that actually makes it to us, we get about 47% of the sun's energy comes to us. So, you know, that's going to heat us up. We get that when we heat us up. Now, if we're heating up, then we're going to emit. So we emit, so some of it gets all the way out, some of it just gets into the atmosphere. And so of what the Earth itself emits, there's about 5% of it makes it out into the atmosphere. And so we've got, what we have is, therefore, that we have a balance. Alright, and the balance is heat in and heat out. Alright, so there's a balance going on between those two things. And if that balance gets out of whack, then the temperature of the Earth will either go up or down. Alright, so, and this is where what's of concern, you know, now to some scientists about, you know, well, how are we actually changing our atmosphere so that the amount of heat that goes out, rather than being 5%, you know, perhaps comes smaller than that. And so that leads us on to what we would term as the greenhouse effect. Alright, so a greenhouse, you know, it's a glass house or some other, and so sun's energy goes through and it gets kept in there, and so inside that house it's warm. So that's what the concern is that might happen with the Earth. And of course, if our temperature goes up, then it goes up too much, life's going to change significantly. So what sorts of things will keep heat in? So water vapour. Carbon monoxide, these sorts of things, methane, nitrous oxide, ozone, which is O3, and chlorofluoro. Carbons. So things with chlorine, fluorine and carbon in them. Alright, so the concern is if we have too many of these things in our atmosphere, then our temperature will go up and that will change life as we know it. Alright, so in the past that hasn't been too concerning at all for anybody, because, you know, in the past the levels have kind of gone up and down, but there's been no significant change. And these come from ice cores in Antarctic in particular, and so they can look at the bubbles in these ice cores, and going back, you know, quite a number of years, thousands of years, and they can look and see what in the bubbles, what the concentration of these particular, in this case carbon dioxide, methane and nitrous oxide, Actually, I've got the formula wrong for nitrous oxide back here, N2O. That's better. And so it's generally up to about here. It's gone reasonably consistent. Yeah, there's fluctuations, but what the concern is now is that nowadays this is what's happening. So the concentration of these three gases is increasing, and so that's with the use of fossil fuels and things like that. So ice cores, that's how we get our information. So the concern is, of course, with the increase of those, then the temperature of the Earth will increase as well. All right, so here's another one, right, and in this picture itself, so this is, here we are today, and these are years before today. Again, these are ice core samples, and looking at the carbon dioxide in the bubbles of air inside these ice core samples. And as you can see, it does go up and down. So sometimes, like in these peak areas, the amount of carbon dioxide is more than in other times. All right, so that's kind of natural that's been happening. But what's been happening in recent times is that the carbon dioxide level is just increasing. All right. Okay, so now moving on to how does the heat move around the Earth. All right, so here's one of the ways. So here's the Earth itself, and we've got our inner core, our outer core, and then we've got the mantle, which is, lava and all that sort of stuff. So, and then here we've got our tectonic plates. So this diagram kind of shows that the magma in the mantle there actually circulates. All right, and so that heat of circulation by convection occurs inside the Earth's crust. So that's one way that heat gets transferred around the Earth. Of course, that's within the Earth, but what about on the Earth's surface itself? Right, well, on the Earth's surface itself, there's ocean currents, and so here's a diagram here that kind of, so you get around Antarctica, we just get some currents, and around the equator, we get some currents, and so those black lines indicating that the temperature of that water, while it's moving around, it's like not moving to a warmer or a cooler area. However, we do get some other currents. So we do get some currents coming down from the north, bringing cool water down. We do get it up from the south, moving the cooler water up. And then, of course, from the equator, both ways, south and north, moving it up. So the warm currents from the equator take the warmer water down towards Antarctica or up towards the Arctic, and then there's currents in the opposite direction. So that helps move heat around the Earth actually on the surface itself. So we've got warm water flowing from the equator to the poles and vice versa. All right. Okay, so that brings us up to problem set number 8. It's in your notes there. So it's about heat moving around the Earth by radiation, convection and conduction, and then those gases that keep the heat in.